So notions of transitivity, reflexivity, and symmetry allow us to define some very special kinds of relations that we could say more about. For example, an equivalence relation. So you all know what equal is, what equivalent is. Well, anything that satisfies the following property is something that behaves like equal, like equivalent. And the properties are three of the ones that we just seen. A binary relation is called an equivalence if it's reflexive, so every element is related to itself. Symmetric, if A is related to B, then B is related back to A. And transitive, if you could get from A to B and you could get from B to C, then you could get from A to C. So if you take a whole Cartesian product of A with itself, you are going to get an equivalence relation, well, which doesn't tell you much. It just says that everything is related to everything, in particular to itself. In particular, things are related back and forth just because they are related. Or if you take the equality relation, so X is related to Y only if X equals to Y, you do get an equivalence relation. It's reflexive, everything's related to itself. It's symmetric. Well, no two different things are related either way. And it's transitive, again, because no two different things are related either way. So the statement of symmetric and transitive are just vacuously true. A more interesting example of an equivalence relation is a mod relation. So X is congruent to Y mod 3 if and only if X and Y have the same remainder when divided by 3. So for example, 5 and 8 both have remainder 2 when divided by 3. And so 5 and 8 are congruent mod 3. Well, every number is congruent to itself mod anything, because if 5 has a remainder 2 divided by 3, then, well, 5 has a remainder 2 divided by 3. So it's reflexive. Is it symmetric? Well, yes. 5 and 8 have the same remainder no matter whether you call it 5 and 8 or 8 and 5. Is it transitive? That's also true, because if 5 and 8 have the same remainder, and 8 and whatever the next thing, let's say 17 have the same remainder, all of them have remainder 2, so all of them are related. So this notion of all of them are related is kind of on the basis of that equivalence relation. Rather than talking about one thing related to the other, with equivalence you could talk about groups of things such that within each group all of them are interrelated. And this is called equivalence classes. So if you have a relation that's equivalence, that is reflexive, symmetric, and transitive, you could split elements of A into groups such that within the groups all elements are interrelated. For example, when we are talking about the mod 3 relation, congruence mod 3, then there are things that are congruent to 0 mod 3. They all have the remainder 0 mod 3. They're all interrelated. Other numbers that have remainder 1 mod 3, again, any two numbers would be related. And the third class would be things, numbers that have the remainder 2 mod 3. And you could notice that every number, every integer either have the remainder 0 or 1 or 2 mod 3. And the number cannot have two different remainders mod 3. So it will fit in exactly one equivalence class. So it can be that there is just one equivalence class. For example, if you take the whole Cartesian product of A with itself, It's a single equivalence class. Everything is related to everything. On the other extreme, if you take the x equals y relation, then every point is an equivalence class on its own because every point is only related to itself and to nothing else. Okay, so equivalence was one example of a type of relation that we could define using notion of reflexive, symmetric, and transitive. But so far we've been missing some of the most common types of relations, like less than or equal. They also have a name. So a relation is an order if it's reflexive and this time anti-symmetric and transitive. So order is definitely not just a complement of an equivalence. And it's not just things that are not symmetric and still reflexive and transitive. It has to be anti-symmetric. It has to be that for every point, the only way they can be related back and forth if it's the same point, if it's the same element. So examples of orders are less than or equal. So x less than or equal to y is reflexive because it's less than or equal. If it's just strictly less than, it's not an order because it's not reflexive. It's anti-symmetric because the only way for x to be less than or equal to y and y to be less than or equal to x is when x and y are indeed the same. And it's transitive because x less than or equal to y, y less than or equal to z. That means that x has to be less than or equal to z. Another example is an alphabetical order of English words, and you could check for yourself that it's anti-symmetric and transitive, and let's just assume that it's reflexive, that every word is related to itself. There are some other interesting examples of orders that are not as linear, so to say, as x less than or equal to y. The relation of being a subset is actually an order because every set is a subset of itself that takes care of the reflexive. If you have two sets A and B, then if A is a subset of B, the only way B can be a subset of A would be if they're equal. That was the definition of being equal, in fact, for sets. And this relation is also transitive because if every element of A is an element of B and every element of B is an element of C, then in particular all the elements of A must be in C because they're in B and everything in B is in C. So being a subset, the relation of subset, the pairs of two, which is pairs of sets A and B such that A is a subset of B, this is an order relation. One more example is divisibility relation. So if every number divides itself, 3 divides 3. If one number divides the other, the only way the second number first can divide second, second can divide first is when they're equal. 5 can divide 5 anyway, but if 5 divides 10, that means that 10 does not divide 5. And finally, for transitivity, if x divides y and y divides z, then x divides z. If 5 divides 10 and 10 divides 20, then 5 divides 20. So this is also an order relation. You may be thinking that parent is an order, but it's not an order for a similar reason, an actually stronger reason, than the strict inequality is not an order. Because a grandparent is not a parent. It's an ancestor, yes, but not a parent. So in order to talk about a relation that's an order, if we mean a family tree and we want to define a relation on a family tree, we need an ancestor relation. And moreover, when you're defining it, in order for it to be an order, we can define every person to be an ancestor of themselves. Why not? It makes things nicer, doesn't cost us anything. So there are two types of orders. As we were saying before, some things are more linear than others. So if when you draw things, they kind of form a line, one comes before two, before three, that's a total order. So if every two elements are related one way or the other, it's a total order. So if you take any two numbers, one of them is going to be less than or equal to the other. If you take any two words, one of them is going to be before the other in the dictionary. Or it may be the same word, that's okay. But if you take subsets, then subsets is not a total order, it's a partial order, because you could have easily two subsets that are not related. 1, 2 and 1, 3 are not subsets of each other. 1, 2 is not a subset of 1, 3, and 1, 3 is not a subset of 1, 2. Both of them are subset of 1, 2, 3, and the set containing just a 1 is a subset of both, but 1, 2, and 2, 3 are not related. So that's what makes it a partial order. Similarly, 5 and 7 do not divide each other, so divisors that we just talked about is a partial order. Similar, ancestor is not a partial order. Two people don't have to be directly related. For two people, one of them doesn't have to be an ancestor of the other. So on this picture of the partial order, it's still transitive, but it's partial because 2 and 3 are not related. So finally, when we talk about orders, one good property of them is that orders may or may not have minimal and maximal elements. There is an order, and we could talk about being minimal and maximal with respect to that order. So what does it mean to be minimal? It means that there are no elements that relate to that element. Well, other than itself, because it's reflexive. For example, if you take natural numbers, well, I don't know if you take natural numbers starting with 0 or with 1, let's say starting with 0, then 0 is your minimal element. It's actually minimum because it's the only minimal element, because nothing is less than or equal to 0. So with respect to the relation less than or equal, 0 is the smallest one. Is there a maximal element in natural numbers? No, because for every element we could get, for every number we could get a bigger number. So if you just look at the relations on 1, 2, 3 that we had before, 1 in both cases was the minimal element and it was the unique minimum. And in the relation R10, we only had one maximal element, it was a 3. And in the relation R11, we had two maximal elements, 2 and 3. So being maximal, it means that, so being minimal means that nothing relates to this element, but this element can relate to others. Being maximal means that this element does not relate to anything else, but things can relate to it. So minimal means no arrows go into it. Maximal means no arrows are coming out except for the loops. So two more interesting cases of minimal and maximal are in subsets where empty set is the minimal or actually unique minimum of the subset relation. Nothing is a subset of empty set except for itself. And the universe is its unique maximum because everything is a subset of universe, but universe is not subset of anything except itself. So here we had the unique minimum and maximum. But if we look at divisors, then we could have a lot of different minimal elements. Actually, divisors have a lot of minimal elements, infinitely many of them, but no maximal, because every prime number is minimal in divisors. Nothing relates to prime, because remember, divisors was x is related to y if x divides y. Nothing except for the number itself divides the prime number. And here we are talking about numbers starting from 2. Otherwise, we would have a unique minimum, which would be 1.